A silent darkness exists where even light cannot escape. This is the event horizon of a black hole, the ultimate point of no return. These cosmic giants are pillars of modern astrophysics, yet they are surrounded by profound and baffling mysteries that challenge our very understanding of reality. You are about to embark on a journey through 30 of the most incredible unsolved questions about black holes and their enigmatic hearts, the singularities. By the end, you will grasp the fundamental conflicts at the edge of physics that keep scientists awake at night. We will explore how information could vanish forever and what might lurk in a singularity's infinite density. No prior expertise is needed for this adventure into the deepest corners of space. What do you think happens to matter when it crosses that final boundary? Our first great mystery begins with a book. Imagine you take a thick novel, a story filled with countless unique words and sentences. You then set it on fire. The paper turns to ash, the ink to smoke. It seems the information is gone, but is it really? According to the unbreakable laws of quantum mechanics, that information is never truly destroyed. In principle, a being with godlike powers could collect every particle of ash and wisp of smoke, reverse the entire process, and reconstruct the book perfectly. The information was merely scrambled, not erased from the universe. Now, take that same book and throw it into a black hole. According to Einstein's general relativity, the book crosses the event horizon and is utterly gone. All its information, every word and letter, is crushed into the singularity and lost forever. The universe, it seems, has forgotten it completely. This is the essence of the information paradox, a devastating conflict made famous by Stephen Hawking. One of our most cherished laws of physics, the law of information conservation, is violated by the very existence of black holes. For decades, this was the standoff. Quantum mechanics insists information is eternal, while general relativity calmly states it is erased. So which one is wrong? A radical idea emerged to solve the impasse, the firewall hypothesis. This terrifying concept suggests the event horizon is not a smooth, silent gateway. Instead, it is a searing wall of unimaginably high energy, a literal firewall that would instantly incinerate anything attempting to cross. The firewall would destroy the information right at the horizon, preserving the quantum law but completely rewriting our picture of what falling into a black hole would be like. It is a violent solution that many physicists find deeply unsatisfying, as it seems to create more problems than it solves. Other theories propose that information is not lost at all, but is somehow encoded on the surface of the event horizon like a hologram, or is slowly leaked back out over millennia through subtle quantum effects. The true resolution remains one of the greatest prizes in theoretical physics. Solving this paradox would not just tell us what happens to a book falling into a black hole. It would force us to discover a deeper, more complete theory of reality, one that can finally reconcile the world of the very small with the realm of gravity and spacetime. This paradox forces us to peer directly into the black hole's terrifying core. At the very center, according to our best equations, lies the singularity. This is not a physical object you could touch. It is a mathematical point of infinite density, where all the mass that has ever fallen into the black hole is crushed into a volume of zero size. Here, the very fabric of spacetime itself curves to an infinite degree, and the laws of physics as we know them simply cease to function. General relativity, the theory that predicts this singularity, also contains the seeds of its own downfall. It cannot tell us what happens in a place where gravity becomes infinite and dimensions lose all meaning. It is a sign that our theory is incomplete. To truly understand the heart of a black hole, we need a new kind of physics, a theory of quantum gravity that can marry the rules of the extremely small with the force of gravity. Without it, the singularity remains a glaring question mark. Is it truly a point of infinite density, or does some new, exotic form of matter halt the collapse? Could it be a bridge, a wormhole connecting our universe to another? Or is it merely a fundamental boundary, a place where our ability to comprehend the universe finally hits a wall? The profound challenge is that the singularity is permanently hidden behind the event horizon. No information, no light, no signal of any kind can ever escape to tell us what it is. We are left with our mathematics and our imagination, staring into an abyss that represents the ultimate limit of human knowledge. So where does that journey of the book or any piece of matter ultimately lead once it crosses the threshold? The classical answer is grim and direct. From the moment something passes the event horizon, every path through spacetime leads inexorably inward toward the center. There is no stopping, no turning back. All matter, whether it is a star, a planet, or an astronaut, is pulled by unimaginable tidal forces. These forces stretch it into a long, thin stream of particles in a process physicists call spaghettification. Everything races toward the singularity, that point of infinite density, and is presumed to be utterly crushed and destroyed. But this is where our understanding fractures. The idea of a true mathematical singularity, a place where physics ends, is so troubling that scientists have proposed radical alternatives. One of the most intriguing comes from string theory, and it is called the fuzzball proposal. This theory completely reimagines the black hole's interior. Instead of a vast, empty space culminating in a tiny, infinitely dense point, a fuzzball suggests the entire region inside the event horizon is a giant, tangled ball of cosmic strings. These are the fundamental threads that, in string theory, make up all particles. There is no smooth spacetime and no singularity. The black hole is a dense, fuzzy ball of vibrating energy, a knot of ultimate complexity. In this view, matter that falls in does not vanish into a singularity. Instead, it simply adds its own threads to the immense, tangled fuzzball, becoming part of its structure. This idea elegantly sidesteps the information paradox. The information about the book that fell in is not lost. It is preserved in the specific, intricate way the new strings are woven into the fuzzball's knot. But what happens to the identity of the matter itself? A star that falls into a black hole possesses specific properties: mass, spin, and electric charge. According to the famous no-hair theorem of classical black hole physics, all other details are erased. The black hole only remembers these three simple numbers. But if information is truly preserved as quantum mechanics demands, then the black hole must somehow retain a perfect, if incredibly complex, record of everything that ever fell in. The fuzzball and other theories suggest that the spin and charge of infalling matter are not just simple numbers on a ledger. They are dynamically woven into the very fabric of the black hole's interior, influencing the vibrations and structure of the fuzzball itself. The journey of matter inside a black hole remains one of the greatest unknowns. Is it a one-way trip to oblivion at a singularity, or a transformation into a new, fundamental state of existence within a fuzzy quantum knot? The answer holds the key to what truly lies within that final darkness. This boundary of no return presents a bizarre duality of experience. From the safety of a distant spaceship, you watch a fellow astronaut pilot their craft toward the black hole. As they approach the event horizon, a strange thing happens. They appear to slow down, their clock ticking ever more slowly compared to yours. Their image freezes, dims, and reddens, stretched into the last photon of light they will ever emit. To you, they never actually cross. They are forever etched onto the surface of the horizon, a fading fossil of a moment in time. But what does the astronaut themselves experience? According to Einstein's pure theory, they would notice nothing special at the moment of crossing. No sign, no flash, no barrier. The event horizon is not a physical wall you can bump into. It is a mathematical boundary in space-time, a one-way street from which there is no U-turn. they would simply fall inward, the universe behind them shrinking into a brilliant disk of light as they are pulled forward by the black hole's immense gravity. This stark contradiction between the outside view and the inside view is a direct result of extreme time dilation, where gravity warps the very flow of time itself. Yet this serene passage is not without its terrors. Long before reaching the central singularity, the difference in gravity between their head and their feet would become catastrophic. These tidal forces would stretch their body into a long, thin stream of atoms, a process as inevitable as it is gruesome. The real debate today is whether this classical picture is correct. Is the event horizon truly this smooth, uneventful mathematical line? Or is it something more physical, like the searing firewall we discussed, that would vaporize the astronaut instantly? The answer changes everything about our understanding of this ultimate frontier. Is it a silent gateway, or is it the end of the line? If our astronaut could somehow survive the journey and pass through the singularity, where would they emerge? This line of questioning leads us to one of the most speculative ideas in all of cosmology, the white hole. In the precise mathematics of general relativity, for every black hole solution, there exists a corresponding white hole solution. Think of it as the complete opposite of a black hole. Nothing can ever enter a white hole from the outside. Instead, it is a region of spacetime that violently expels matter and energy, a cosmic fountain of infinite pressure that spews light and material outward, forever unreachable. It is the ultimate exit door with no entrance. One captivating theory suggests that a black hole and a white hole could be connected, forming opposite ends of a tunnel through spacetime known as a wormhole. In this fantastical picture, our astronaut, after falling into the black hole, would not be crushed but would instead travel through this bridge and be ejected out of the white hole into a completely different region of the universe, or even into a different universe entirely. Another profound idea posits that our own Big Bang, the explosive birth of everything we know, could have been the violent eruption of a primordial white hole. Yet for all their mathematical elegance, white holes face a monumental problem. No one has ever seen one. We have no observational evidence whatsoever for these cosmic gushers. The reason lies in the second law of thermodynamics, the universal rule that disorder always increases. A white hole, by its very nature, would be a place of incredibly high order, a perfectly organized eruption that seems to defy the natural tendency of the universe toward chaos. Most physicists believe that while white holes are beautiful solutions on paper, they are thermodynamically unstable and would almost instantly collapse into something else, perhaps even transforming into a black hole the moment they tried to form. So they remain in the realm of tantalizing possibility, a ghost in the equations that hints at a universe far stranger than we can currently prove. The sheer scale of these cosmic giants defies easy explanation. Scattered at the centers of nearly every large galaxy, including our own Milky Way, are supermassive black holes, colossal entities weighing millions or even billions of times more than our Sun. Their existence presents a profound timing problem. Astronomers have spotted incredibly bright, distant quasars, the blazing beacons of matter falling into supermassive black holes, shining from when the universe was less than 1 billion years old. How did such monstrous objects grow so immense so quickly? The universe simply did not seem to have enough time to build them. This is the great mystery of their origin, and scientists are exploring several compelling pathways. One theory suggests a dramatic birth, where enormous, pristine clouds of gas in the early universe collapsed directly under their own immense weight. In this scenario, the gas cloud would bypass the stage of forming normal stars entirely, instead condensing into a supermassive black hole in one single catastrophic event. This would create a ready-made heavyweight seed, tens of thousands of solar masses from the very beginning, giving it a massive head start. Another possibility is that the seeds were much smaller, perhaps the remnants of the first generation of colossal stars. These stellar mass black holes would then have needed to grow at an astonishingly rapid rate, feasting on the dense gas that filled the early cosmos. This would require them to eat at or even above their theoretical maximum limit for billions of years, a frenzied binge that challenges our understanding of black hole appetites. A third path involves a chaotic dance of mergers where countless smaller black holes and stars in a dense cluster collided and combined, slowly building up mass over time through a series of violent unions. Each of these theories has its own strengths and weaknesses. The direct collapse model can explain the rapid appearance of the heaviest black holes, but it requires very specific, pristine conditions that might have been rare. The rapid growth from small seeds is a more gradual process, but it struggles to explain the most distant, most luminous quasars we see. Their light, which has traveled to us for over 13 billion years, tells us that supermassive black holes were not just present in the infant cosmos, they were already fully grown and dominating their galactic environments. This forces us to reconsider the entire timeline of cosmic structure formation. Did galaxies form first, and then their central black holes grew within them? Or did the black holes form first, acting as gravitational anchors around which the very first galaxies coalesced? The answer is written in that ancient light, a message from the dawn of time that we are only just beginning to decode. The violent death of a massive star presents the universe with a stark choice. If the collapsing core is too heavy to be supported by any known force, it will plunge past all limits and form a black hole. But if its mass falls just below that critical threshold, it can achieve a strange and stable equilibrium, becoming a neutron star. Imagine taking the entire mass of our Sun and crushing it into a sphere the size of a city. The result is a neutron star, an object so dense that a single teaspoon of its material would weigh billions of tons. It is a failed black hole, a cosmic entity that stared into the abyss but stopped just short of the final collapse. This existence is incredibly precarious. The neutron star is held up by a quantum mechanical force called neutron degeneracy pressure, a last-ditch rebellion against gravity's relentless pull. Add just a little more mass, perhaps by siphoning gas from a companion star or through a cataclysmic collision, and this delicate balance shatters. The star can no longer support its own weight, and it crosses the threshold, collapsing silently and completely into a black hole. The boundary between these two states of matter is razor-thin, a line drawn by the laws of physics that separates a visible, albeit bizarre, object from an invisible gravitational prison. We have now witnessed the moment this line is crossed in the most dramatic way possible. Through the collisions of these incredible objects, gravitational wave observatories have felt the space-time ripples from neutron stars crashing into black holes. In these events, the black hole, being far more massive, acts like a cosmic shredder. Its immense tidal forces tear the neutron star apart, pulling it into a swirling, incandescent stream before swallowing it whole. But sometimes the collision might not be so one-sided. If the black hole is small and the neutron star is particularly massive, the merger might create something even more fleeting and mysterious. For a few fleeting milliseconds, the combined object could form a hypermassive neutron star, a single entity so massive and dense that it should instantly collapse, yet it is temporarily held together by its incredibly rapid spin. This is a star living on borrowed time, a dizzying cosmic dance that cannot last. It spins itself apart, and in its final moment it collapses, giving birth to a new, slightly larger black hole. These collisions are cosmic laboratories, creating conditions of density and temperature impossible to replicate on Earth. They might be forging new, exotic states of matter, like strange quark matter, where the very protons and neutrons themselves dissolve into a soup of their fundamental components. Every ripple in spacetime from such an event carries the secret of what matter becomes at the very edge of existence. Stephen Hawking turned this entire picture on its head with a stunning revelation. Black holes, he declared, are not perfectly black, they glow. they possess a faint temperature and slowly, imperceptibly radiate away their mass into the void. This phenomenon, now known as Hawking radiation, arises from the bizarre and probabilistic world of quantum mechanics. Empty space is not truly empty. It is a seething, bubbling sea of virtual particles. These are particle and anti-particle pairs that spontaneously pop into existence from the raw energy of spacetime, borrowing energy from the universe for an impossibly brief moment before they collide and annihilate, paying back the energy loan. This frantic activity happens everywhere all the time, but at the very edge of a black hole's event horizon, this quantum dance takes a tragic turn. Imagine one of these virtual pairs appearing right at the precipice. In a fantastical stroke of bad luck, one particle falls inward, crossing the horizon, while its partner is flung outward, escaping the black hole's grip. The escaped particle becomes real, stealing a tiny amount of energy from the black hole to pay its debt to the universe. From the perspective of a distant observer, the black hole has just emitted a particle. To conserve energy, the black hole itself must lose a minuscule amount of mass. The particle that fell inward, however, has a negative energy relative to the outside universe. When it joins the black hole, it effectively reduces the black hole's total mass and energy. This is an excruciatingly slow drip of leakage. For a black hole with the mass of our Sun, the temperature of this Hawking radiation is colder than the cosmic background glow of the universe itself. It would take longer than the current age of the universe to evaporate even a fraction of its mass. But for the very smallest theoretical black holes, or for all black holes in the far, far future when the universe has expanded and cooled, this process becomes their death sentence. As the black hole radiates, it loses mass. As it loses mass, it shrinks. As it shrinks, its temperature increases, causing it to radiate even faster. In the final moments of its life, this evaporation would accelerate into a runaway process, culminating in a possible flash of high-energy radiation, a final whisper signaling its complete disappearance from reality. This leads us back to the information paradox with even greater force. If a black hole evaporates entirely, what happens to all the information about every star, planet, and book that ever fell in? Does it vanish forever when the black hole pops out of existence, violating quantum law once and for all? Or is that information somehow encoded in the Hawking radiation itself, a scrambled, nearly impossible to decode message broadcast into the cosmos? The search for that answer continues, buried in the faint, cold glow of a dying black hole. Hawking's prediction of a glowing, shrinking black hole leads to an inevitable and startling conclusion. If this process continues unimpeded, the black hole will eventually vanish. But what does that final moment look like? As the black hole evaporates, it shrinks and its temperature soars. In its last fleeting second of existence, a black hole with the mass of a small mountain would glow with the brightness of a billion suns, unleashing its pent-up energy in a final, catastrophic burst. It would be a spectacular cosmic firework, a silent, brilliant flash marking the end of a gravitational titan. Yet this dramatic finale is fraught with deep theoretical problems. One major issue is the trans-Planckian problem. Hawking's original calculation relies on quantum particles with wavelengths longer than the black hole itself at the very end of its life. But as the black hole shrinks to a microscopic size, the radiation it emits would require particles with impossibly high energies, energies that far exceed the Planck scale, the point where our current laws of physics completely break down. We simply do not know how to describe physics in such an extreme regime. This suggests that Hawking's elegant calculation, while brilliant, may not be the final word on how black holes truly die. Another possibility is that evaporation stops just short of nothing. The black hole might shrink down to a tiny, stable relic with a mass around the Planck mass, a minuscule speck weighing about 20 micrograms. This remnant would be a fossil, a permanent tombstone containing all the information that ever fell into the original black hole, forever locked away in an object too small and dense to ever probe. But this, too, creates a paradox. Such a remnant would have an enormous density crammed into a tiny volume, essentially creating a new kind of singularity and raising the same questions about infinite curvature that we hope to avoid. The most profound challenge, however, is that we have never seen it happen. Hawking radiation has never been observed. The glow from stellar mass black holes is trillions of times colder than the cosmic microwave background, utterly drowned out by the warmth of the universe. We cannot create black holes in a lab to watch them decay. The entire life cycle of a black hole, from its fiery birth to its theoretical silent evaporation, remains a majestic story written in mathematics, waiting for a single, confirming spark of light from the cosmos to prove it is real. This cosmic family portrait has a glaring gap. We have discovered countless stellar mass black holes, the remnants of dead stars weighing between a few and perhaps 100 times our Sun. And we know supermassive black holes, the billion solar mass giants, rule the centers of galaxies. But what lies in the vast chasm between them? For decades, the search for intermediate mass black holes, those weighing from a few hundred to a few 100,000 solar masses, has turned up mostly empty. It is as if the universe skipped a crucial step in its building process, creating small houses and immense castles with nothing in between. This is the hierarchy problem, a puzzle that challenges our models of how cosmic structures grow. How do the supermassive black holes get so big if there are no middleweight seeds for them to consume? Without these stepping stones, the giants would have to form almost impossibly fast. The hunt for these missing links has been difficult because they are dark and quiet. A lone intermediate black hole with no nearby stars to rip apart and consume emits no telltale X-ray shriek to grab our attention. But our methods of detection are becoming more sophisticated. Astronomers have looked for the subtle, telltale sway of stars orbiting an invisible, massive object within a dense globular cluster. A few candidates have emerged from this painstaking work, stars whirling around a dark heart with the gravitational pull of thousands of suns. More recently, a new window has opened with gravitational wave astronomy. The ripples in spacetime from colossal collisions have delivered tantalizing hints. Some of the black holes detected merging are suspiciously heavy, falling right into that elusive intermediate mass range. These are not the simple remnants of a single star's death. They are themselves likely the products of previous mergers, black holes that cannibalized others in a dense stellar environment to bulk up. Each gravitational wave signal is a snapshot of a black hole family tree, and some of these trees appear to have intermediate mass roots. Finding a definitive population of these middleweight black holes would be a monumental discovery. It would validate the idea of hierarchical growth, where black holes start small and steadily gain mass through a diet of gas and stellar mergers. They would be the missing seeds, the crucial intermediate step that explains how a modest stellar corpse can, over billions of years, blossom into the supermassive monarch of a galaxy. Their very existence would weave a continuous story from the death of a star to the birth of a cosmic giant. This radical simplification of reality is known as the no-hair theorem. It suggests that a black hole, no matter how complex the star or the galaxy that fell into it, is ultimately defined by just three numbers: its mass, its spin, and its electric charge. Everything else, every detail, every atom, every chapter of the book we threw in, is permanently erased. A black hole has no hair, no distinguishing features beyond this bare trio of properties. It is the ultimate cosmic amnesiac. This theorem presents a universe of profound simplicity, but also one of terrifying loss. Imagine two black holes with identical mass, spin, and charge. According to this principle, they would be completely indistinguishable, even if one was born from a quiet, solitary star and the other from a chaotic mixture of 1,000 different planets and asteroids. All of that rich, complex history is gone, shaved away by the event horizon. This elegant idea, however, is now under serious assault. The central conflict returns to the information paradox. Quantum mechanics insists that information cannot be destroyed, so it must be somewhere. If the no-hair theorem is correct, then quantum mechanics must be wrong, a conclusion most physicists are deeply reluctant to accept. This has led to the search for black hole hair, subtle structures or properties that could encode the missing information. In alternative theories of gravity, like string theory or certain modified gravity models, black holes might not be so bald after all. They could possess a faint fuzz of additional quantum fields, a kind of gravitational hair that records what fell in. This hair would not be a physical mane you could see, but rather an intricate pattern woven into the fabric of the event horizon itself, a complex hologram storing the history of everything the black hole has consumed. Detecting such hair would require observing the most delicate vibrations of a black hole, the specific way it rings like a bell after a collision. The precise tones of this ringing, its quasi-normal modes, could carry the signature of these hidden properties. If two black holes that look identical from the outside according to the no-hair theorem actually ring with subtly different frequencies, that would be the smoking gun, proof that they remember their past. The hunt is on to see if black holes are the simple, forgetful beasts of classical physics, or if they are cosmic librarians, meticulously preserving every single detail of their history in a code we are only just beginning to crack. This elegant simplicity of a black hole's memory depends entirely on a cosmic rule, an unspoken law that many physicists believe keeps the universe from descending into chaos. Roger Penrose proposed this principle, known as the cosmic censorship hypothesis. It is the bold conjecture that nature abhors a naked singularity. The idea is that every singularity, that point of infinite density where physics breaks down, must always be hidden from our view, permanently cloaked behind the protective veil of an event horizon. This horizon acts as a cosmic censor, shielding the rest of the universe from the unpredictable and lawless physics that would reign at the singularity. Without this censorship, the very foundation of predictability in science would be threatened. The ultimate cause and effect would shatter. Now consider the terrifying alternative, a naked singularity. This is a gravitational monster without a cage, a point of infinite density exposed to the rest of the universe. From such an object, anything could emerge. The known laws of physics would offer no guide. It could unpredictably spew out concentrated beams of radiation, or even entire new universes without any warning or reason. The cosmic censorship hypothesis asserts that this simply cannot happen. The universe, in its wisdom, has built a mandatory prison for these mathematical monsters, ensuring they can never influence the orderly cosmos outside their walls. Most physicists believe this hypothesis is true, not necessarily because it is proven, but because the alternative is so unpalatable. A universe with naked singularities would be a universe where we could never reliably predict the future based on the past. Yet the conjecture has never been definitively proven. There are potential counterexamples in the complex mathematics of general relativity. For instance, if a black hole is spinning fast enough, some solutions suggest its event horizon could shrink away to nothing, leaving the singularity exposed. Or during the chaotic collapse of a highly asymmetrical, non-spherical star, a singularity might form without a horizon ever fully enveloping it. So far, no conclusive evidence for such an object has ever been found. The search continues because the stakes could not be higher. If we were ever to observe a naked singularity, it would be the most profound discovery in the history of physics. It would not just be finding a new type of object, it would be witnessing the complete and public breakdown of predictability in our universe. The event horizon is more than a boundary of no return. It is the final firewall protecting the rational order of reality from the infinite insanity lurking at its core. This strange connection between thermodynamics and black holes leads us to an even more profound enigma. Black holes have entropy. They possess a specific, measurable amount of disorder. This was a stunning discovery because entropy is a property of systems with many constituent parts, like the countless molecules in a gas. A black hole, according to the no-hair theorem, was supposed to be the simplest object in existence, defined by just 3 numbers. How could something so simple have such immense disorder? The answer lies not in the volume of the black hole, but on its surface. Jacob Bekenstein and Stephen Hawking found that a black hole's entropy is directly proportional to the area of its event horizon. Think of it this way. If you have a box full of gas, the number of ways you can arrange the gas molecules, its entropy, depends on the volume of the box. A bigger box means more possible arrangements, but for a black hole, the entropy depends only on the surface area of its boundary, not on the vast, mysterious space inside. This is completely counterintuitive. It suggests that all the information needed to describe the 3-dimensional contents of a black hole might be perfectly encoded on its 2-dimensional event horizon, like a cosmic hologram. A hologram is a perfect analogy. Look at a credit card hologram, a flat, 2-dimensional surface. When you tilt it, it displays a full 3-dimensional image. The information for that entire 3-dimensional scene is stored on the 2-dimensional plastic. The holographic principle applies this mind-bending logic to the entire universe, proposing that reality, with all its 3-dimensional richness, might be a projection from a 2-dimensional information field stored at its boundary. A black hole is the simplest place to see this principle in action. Every particle, every bit of energy that falls in, increases the area of the event horizon just a tiny bit. That increased area corresponds to an increase in entropy, as if the black hole is adding a new pixel to its surface to record the new information. This creates a deep and unexpected bridge between the 3 great pillars of physics. Thermodynamics gives us entropy and the laws of heat. Gravity, through Einstein's theory, defines the geometry of spacetime and the area of the horizon. And quantum mechanics provides the bits of information that are being encoded. The black hole entropy enigma forces these 3 disparate languages to talk to one another, suggesting they are all different facets of a single, deeper truth. Unlocking why a black hole's interior is described by its surface could be the final key to a theory of everything, a single equation that finally unites the cosmos and the quantum. Even the darkest objects in the cosmos can become beacons of unimaginable power. From the poles of some feasting black holes, colossal jets of energy erupt, stretching for millions of light years across the intergalactic void. These are not random sprays of material, but tightly focused beams of radiation and particles accelerated to almost the speed of light. They are cosmic blowtorches, and their origin is one of the most dynamic puzzles in astrophysics. The fuel for these jets comes from the accretion disk, the swirling whirlpool of superheated gas and dust that spirals into the black hole. But this material does not all fall in. Near the event horizon, the black hole's ferocious rotation and immensely powerful magnetic fields act like a colossal engine. The spinning spacetime of the black hole, an effect known as frame dragging, winds up these magnetic field lines, twisting them into a tightly coiled structure. This creates a powerful funnel that captures some of the infalling material and, with incomprehensible force, blasts it outward along the black hole's rotational axis, the path of least resistance. The exact trigger for this launch remains hotly debated. One leading theory suggests that the jet is powered directly by the black hole's spin, essentially stealing rotational energy from the monster itself. Another posits that the intense turbulence and magnetic fields within the inner accretion disk are the primary driver. The mystery deepens when we observe that not all black holes produce these jets. 2 black holes with similar mass and spin can reside in similar galaxies, yet one will unleash these brilliant lances into space while the other remains dark and quiet. This suggests that smaller scale, local conditions in the accretion disk, perhaps the precise configuration of its magnetic fields or the rate at which gas is being fed to the black hole, act as a hidden switch. The presence or absence of a jet might come down to a subtle, chaotic dance of physics happening just outside the point of no return. Understanding these jets is crucial as they have a profound impact on their surroundings. They pump enormous energy into intergalactic space, heating vast clouds of gas and regulating the formation of new stars in their host galaxy. They are architects of their cosmic environment, and deciphering their ignition sequence means understanding one of the most fundamental feedback loops in the evolution of our universe. These cosmic jets and the supermassive black holes that power them are dominant forces within the visible universe. But what about the components we cannot see? The story of black holes becomes even more enigmatic when we consider their potential relationship with the universe's two greatest ghosts, dark matter and dark energy. Most of the matter in the cosmos is dark, an invisible substance that reveals itself only through its gravitational pull. We are surrounded by a vast sea of it, so it is only logical to ask, do black holes eat dark matter? The answer is not straightforward. Unlike normal matter, dark matter particles are thought to interact with each other and with regular matter almost exclusively through gravity. They do not collide, radiate, or form an accretion disk. This means a black hole could only feast on dark matter through direct capture, a terribly inefficient process. A dark matter particle would need to be on a trajectory that sends it straight through the event horizon, a very rare bullseye. This suggests that dark matter contributes very little to a black hole's diet and growth. Yet, this very inefficiency could be the key to finding it. Some theories propose that dark matter particles can accumulate in the dense core of a black hole, forming a spike of incredibly dense dark material. The gravitational waves from a black hole merger might carry a subtle imprint of this dark matter spike, a faint signature of the invisible universe. An even more radical idea suggests that dark matter itself might be made of black holes. Not the giant ones we see today, but primordial black holes, tiny entities that could have formed from the intense density fluctuations in the first moments after the Big Bang. These hypothetical black holes, some no larger than an atom but with the mass of a mountain, could be swarming throughout the cosmos, completely unseen. If they exist in sufficient numbers, they could account for all the dark matter whose gravity binds galaxies together. The connection stretches to the largest scales of all with dark energy, the mysterious force driving the universe's accelerated expansion. One highly speculative but fascinating theory links this cosmic repulsion directly to black holes. The vacuum of space is not empty, it contains a fundamental energy. Could it be that the immense volumes inside black holes, specifically the vacuum energy at their singularities, are somehow connected to dark energy? As black holes form and grow across cosmic history, are they somehow seeding the universe with this repulsive force, tying the fate of the smallest points of infinite density to the accelerating fate of the entire cosmos? This idea remains on the fringe of physics, but it highlights a profound quest to find a single thread that connects the ultimate prisons of gravity to the invisible scaffolds of the universe and the very fabric of spacetime itself. Our universe is made of matter, but we have never found a convincing reason why. Every known physical process creates matter and antimatter in perfect, equal pairs. When they meet, they annihilate in a flash of pure energy. According to this perfect symmetry, the Big Bang should have produced equal amounts of both, leaving behind a cosmos filled with nothing but radiation after a grand mutual destruction. Yet here we are, in a universe full of planets, stars, and galaxies, all made from the matter that somehow, against all odds, survived. This is the Baryon asymmetry problem, and its solution might be hidden in the most destructive places imaginable. Black holes could be the ultimate cosmic vandals, smashing the fundamental symmetries of nature. The laws of physics, as we understand them, are built on certain sacred principles, like the conservation of baryon number, which essentially states that the total amount of matter in the universe should remain constant. But a black hole does not play by these rules. When matter falls into a black hole, it carries its baryon number with it, a number that should be preserved. However, when that black hole later evaporates via Hawking radiation, it does not seem to give that matter back. It radiates a random mix of particles and antiparticles, paying no heed to the original ledger. The black hole has effectively erased the baryon number, violating a fundamental conservation law. This is not a bug, it is a feature of their ruthless gravitational dominance. Theoretically, if a black hole can destroy this symmetry, it could also create a slight imbalance. Certain theories, including some extensions of the standard model of particle physics, suggest that the extreme conditions around a black hole, or within its Hawking radiation, could favor the production of matter over antimatter by a tiny, almost imperceptible fraction. Now scale this idea up to the dawn of time. Imagine the early universe teeming with countless primordial black holes, tiny gravitational pits formed in the seething chaos of the first second. These black holes would have been evaporating furiously, their lives short and violent. As each one evaporated and vanished, it would have released a final burst of particles. If their evaporation process inherently favored matter over antimatter, even by just 1 part in a billion, then these countless tiny explosions could have collectively seeded the entire cosmos with the slight excess of matter we see today. In this breathtaking scenario, black holes are not just cosmic destroyers. They are the unlikely sculptors of existence itself, their silent, quantum-level prejudice responsible for every atom, every star, and every life form in the universe. The very fact that we are here to ponder them might be their most profound and lasting legacy. A spinning black hole is a cosmic vortex, twisting the fabric of spacetime itself into a vortex we call a Kerr black hole. Unlike its simpler, non-spinning cousin, this rotation creates a bizarre region just outside the event horizon known as the ergosphere. Here, the drag of spinning spacetime is so powerful that nothing can stand still, not even light. Everything is forced to move in the direction of the spin, a celestial whirlpool of ultimate force. This rotation unlocks a phenomenon as strange as it is powerful: superradiance. Imagine tossing a wave, any wave, toward this spinning monster. If the wave has the right frequency and enters the ergosphere, a remarkable theft can occur. The rotating black hole can impart energy to the wave, amplifying it as it scatters. The wave rebounds with more energy than it arrived with, having stolen a tiny fraction of the black hole's rotational momentum. It is like a skilled tennis player returning a serve with added topspin, using the ball's own energy against it, but on a cosmic scale. This process slowly breaks the black hole's spin, converting its rotational energy into a more powerful outgoing wave. But what if this energy extraction could run wild? This is the heart of the stability mystery. Theoretical studies suggest that under certain conditions, this superradiant scattering could trigger a runaway instability. If the amplified waves become trapped by a surrounding force field, perhaps from a speculative particle like an action, they could bounce back and forth, growing exponentially in a positive feedback loop of terrifying power. The waves would extract more and more rotational energy, potentially shaking the black hole apart. The very object we think of as the most stable gravitational pit in the universe could, in theory, be shattered by the amplified echoes of its own rotation. This is not just a mathematical curiosity, it is a direct assault on the robustness of general relativity. The theory predicts that Kerr black holes should be stable, but these potential instabilities probe the very limits of that prediction. How can we test such a fantastic idea? The answer lies in listening to the cosmos. Gravitational wave observatories are our stethoscopes on the heart of spacetime. When two black holes merge, the final single black hole does not simply sit in silence. It rings, vibrating at specific frequencies as it settles down. These quasi-normal modes are the unique signature of the final object's mass and spin. If a Kerr black hole were truly unstable, the gravitational wave signal from such a merger would reveal anomalous, sustained ringing, a dissonant chord that refuses to fade away as expected. Finding no such instability so far actually reinforces our confidence in Einstein's theory, but the search continues for any tiny deviation, any whisper of a fracture in our understanding of these spinning giants. The violent evaporation of countless small black holes could have tipped the cosmic scales, but where did these gravitational specks come from in the first place? The answer may lie in the universe's very first instant. Within a fraction of a second after the Big Bang, the entire cosmos was a seething, turbulent ocean of energy. In this primordial fury, random density fluctuations could have created pockets of space so incredibly dense that they collapsed under their own weight, not into stars but directly into black holes. These are the primordial black holes, and they are nothing like the ones we see today. They could have been any size, from smaller than a single atom yet with the mass of a mountain, to large enough to rival the heft of an entire star. Their formation bypassed the need for stellar death, making them ancient relics from the universe's explosive birth. This simple yet powerful hypothesis offers elegant solutions to some of our greatest cosmic puzzles. The most compelling is the mystery of dark matter. We know it exists by its gravitational pull, but we have never detected a single particle of it. What if dark matter is not a sea of exotic particles at all, but a vast, unseen swarm of these primordial black holes, drifting like invisible asteroids through the emptiness of space? If they are numerous enough, their collective gravity could perfectly explain why galaxies hold together and rotate the way they do. Furthermore, these ancient black holes could solve the timing problem of the supermassive giants. A hefty primordial black hole formed with a mass of tens of thousands of suns would have been the perfect seed, placed directly into the infant cosmos, ready to gorge on surrounding gas and quickly grow into the supermassive rulers we see at the hearts of galaxies. The hunt for these ghostly objects is a masterclass in cosmic detective work. Astronomers search for their fleeting shadows through a phenomenon called microlensing. If a primordial black hole drifts precisely between us and a distant star, its gravity will act as a lens, bending the star's light and causing it to momentarily brighten in a very specific way. We have seen such events, but confirming they are caused by black holes and not dim stars or rogue planets is the challenge. Another method is to listen for their final moments. The very smallest primordial black holes should be evaporating right now, ending their lives in a burst of high-energy radiation, a gamma-ray flash we could potentially detect. And as they merge, they would create a chorus of high-frequency gravitational waves, a signature completely distinct from the mergers of stellar mass black holes. Finding just one would be a monumental breakthrough. It would prove that black holes can form without stars, rewrite the story of dark matter, and open a direct window into the conditions of the universe in its very first second of existence. These tiny gravitational fossils hold the potential to connect the largest structures in the cosmos to the very moment of its creation. The swirling chaos of the primordial black hole leads us to the most dizzying possibility of all. What if the cosmos we call home, with all its galaxies and stars, is itself nestled within the ultimate cosmic prison? This is the black hole universe hypothesis, a concept that stretches the imagination to its absolute limit. The idea begins with a haunting mathematical echo. The equations that describe the initial singularity of the Big Bang, a point of infinite density from which our universe erupted, bear a striking resemblance to the equations for the singularity at the heart of a black hole. Both are points where general relativity breaks down, where density and curvature become infinite. This similarity is not proof, but it is a provocative clue. The theory then takes this parallel and flips it completely. If our universe began in a state like a black hole singularity, then what we experience as cosmic history might not be an explosion outward, but rather an expansion inward. Think of a white hole, the theoretical opposite of a black hole. Nothing can enter a white hole, it only expels matter and energy. Our universe's relentless expansion, with every galaxy flying away from every other, looks mathematically similar to the interior of a colossal white hole. In this mind-bending picture, our entire observable cosmos exists inside the event horizon of a black hole belonging to a vastly larger parent universe. The Big Bang was not a fiery birth in a void, but the moment this parent black hole formed, with our universe unfolding within its hidden depths, the philosophical implications are staggering. It suggests a cosmic Russian nesting doll, an infinite regression of universes within black holes within still grander universes. Every black hole that forms in our cosmos could, in this view, contain an entire new universe within its singularity, a full cosmos with its own laws of physics, stars, and perhaps even life. This offers a bizarre kind of cosmic selection, where universes that produce the most black holes are the ones that spawn the most descendant universes. The theory remains firmly on the fringe of cosmology because it is, for now, virtually untestable. The event horizon that defines our cosmos would lie beyond the limit of what we can observe, a boundary we could never cross or see past. Any signal we could possibly detect originates from within our own cosmic bubble, yet it persists as a fascinating thought experiment, forcing us to confront the deepest questions about our reality. Is our universe a unique, solitary creation, or is it merely one cell in an infinite, self-replicating cosmic organism? The answer, if it exists, is locked behind the ultimate veil. Deep within the intense flicker of a feeding black hole lies a rhythmic secret. As matter spirals inward in its final, frantic dance, the blazing X-ray light it emits does not simply flare at random. It often pulses with a strange, nearly regular beat, a cosmic drumming that speeds up and slows down in a tantalizing pattern. These are quasi-periodic oscillations, or QPOS, and their origin is one of the most active puzzles in high-energy astrophysics. The rhythm is not perfectly steady like a metronome, hence the term quasi-periodic. It is a stutter, a wobble, a signal that something fundamental is happening in the last stable orbits before the point of no return. Scientists believe these oscillations are linked to the natural frequencies of spacetime itself, set by the black hole's immense gravity. Imagine a marble rolling around a deep funnel. The marble has a natural frequency for completing a full orbit. It also has a different frequency for wobbling up and down on the rim. Near a black hole, matter behaves in a similar way but governed by Einstein's laws. The flickering X-rays are thought to be a direct reflection of these orbital and vertical frequencies, the fundamental notes of matter's death spiral. The grand debate is over what physical process actually creates the flicker we see. Is it a hotspot, a single, dense clump of material whipping around in the inner accretion disk, blinking like a lighthouse beam with each orbit? Is it the entire inner edge of the disk oscillating like a drumhead, vibrating in and out as it is stretched by tidal forces? Or are powerful magnetic fields, wound to breaking point by the black hole's spin, snapping and reconnecting in a regular, explosive rhythm, lighting up the surrounding gas? The answer matters profoundly because these oscillations offer a potential direct measurement of a black hole's properties. If we can definitively link the observed frequencies to the predicted orbital speeds and frame dragging effects of general relativity, then QPOS become a powerful tool. They would act as a natural laboratory for studying strong gravity, allowing us to test Einstein's theory in its most extreme regime and even map the precise space-time geometry right at the edge of the event horizon. Each flicker is a coded message from the precipice, a rhythmic key that could unlock the final, violent motions dictated by a black hole's relentless pull. Two supermassive black holes drift together in a cosmic dance that should end in a cataclysmic merger, yet they often freeze. When the cores of two galaxies collide, their central black holes are drawn toward one another, sinking to the shared center of the new, larger galaxy. They spiral closer and closer, but then something strange happens. At a distance of about 1 parsec, roughly 3.26 light-years, their inward journey grinds to a halt. They are still gravitationally bound, but they cannot get any closer. This is the final parsec problem, a stubborn dynamical puzzle that prevents these giants from uniting. The issue is a lack of friction. To spiral inward, the black holes must shed their immense orbital energy, but in the near vacuum of galactic centers, there is very little to slow them down. They have already pushed away or consumed most of the nearby stars through a process called dynamical friction. At the final parsec, they are left orbiting each other in a vast, empty ballroom with no way to lose the energy needed for their final embrace. Without a solution to this standoff, they would remain locked in a binary system for billions of years, never merging. This presents a major problem for our models of galaxy evolution and for our future observations. How do they finally overcome this last barrier? One proposed solution involves a third actor in this gravitational play. If another supermassive black hole is drawn into the dance, its chaotic influence can disrupt the stable orbit of the binary pair. The three-body interaction can fling one of the black holes inward, providing the precise kick needed to bypass the final parsec and trigger a merger. Another possibility lies in the presence of vast reservoirs of gas. If a circumbinary disk of gas remains from the galactic collision, the black holes can plow through it, creating spiral density waves that act like a gravitational brake, sapping their orbital energy and drawing them relentlessly together. The resolution of this mystery is crucial for predicting the chorus of gravitational waves that should ripple from such colossal unions. Future space-based observatories are designed to listen for these low-frequency ripples, the deepest notes in the cosmic symphony. If supermassive black holes routinely stall at the final parsec, that symphony could be far quieter than we expect. Their silent standoff holds the key to understanding how the largest structures in the universe ultimately come together. These ghostly cosmic messengers may hold secrets from the very edge of oblivion. Neutrinos are among the most elusive particles in existence, streaming through the universe in untold trillions, passing through entire planets as if they were empty space. They interact with matter so rarely that they are often called ghost particles. Yet, when a neutrino is born under conditions of unimaginable violence, it can carry energies millions of times greater than those produced in our most powerful particle colliders. The most extreme environments in the cosmos are needed to create such high-energy astrophysical neutrinos, and there are few places more extreme than the turbulent maelstrom surrounding a feeding black hole. Deep beneath the ice at the South Pole, the Ice Cube Neutrino Observatory has detected these rare, high-energy messengers, and their paths seem to point back to cosmic powerhouses like supermassive black holes at the hearts of active galaxies. When a black hole shreds a star or powers its colossal jets, the chaotic forces involved could be accelerating protons to near light speed. These protons then collide with other particles, creating a cascade that ends with the birth of a high-energy neutrino. This ghostly particle then flies across the universe in a perfectly straight line, unaffected by magnetic fields, carrying a pristine message from the heart of the cataclysm. This leads to a profound speculative question. Could neutrinos be doing more than just carrying energy away? Could they be carrying information? During the violent collapse that forms a black hole, the intense pressures and densities might generate a tremendous burst of neutrinos. If information is not truly lost inside a black hole, perhaps some of it is imprinted onto the properties of these escaping neutrinos, a final broadcast from the collapsing star before the event horizon permanently seals it away. Similarly, during the final stages of black hole evaporation via Hawking radiation, the last bursts of energy could produce particles including neutrinos. If these neutrinos retain any correlation with the original material that fell into the black hole, they could be the key to solving the information paradox, acting as tiny, nearly undetectable messengers from a dying black hole's memory bank. Their unique properties offer an even more tantalizing possibility. Since neutrinos barely interact with anything, they could, in theory, travel directly from regions that are completely opaque to light. A photon from the inner accretion disk is absorbed and re-emitted countless times before it finally escapes, its origins blurred. But a neutrino could be born deep within the powerful magnetic fields just outside the event horizon and fly straight out, offering a clean, direct signal from the very brink. This raises a truly radical thought. Could a neutrino, under some bizarre quantum gravitational effect, even be created inside the event horizon and still escape? It seems to defy the fundamental rule of black holes, but the quantum nature of both neutrinos and spacetime itself might allow for a tiny probability of such an event. If so, a neutrino could be our only possible physical probe of the interior, a ghostly spy returning from behind the ultimate curtain. Observing high-energy neutrinos in coincidence with gravitational waves and light from the same cosmic event would open a completely new window onto black holes, a multi-messenger view of the most destructive phenomena in the universe. These silent, almost massless particles may be whispering the deepest secrets of gravity's ultimate dominion. The faintest whisper of structure might cling to the black hole's surface. This is the concept of soft hair, a delicate and beautiful idea that suggests black holes are not perfectly bald after all. The term soft hair refers to an incredibly subtle fuzz made of zero-energy particles, photons or gravitons that could adorn the event horizon. These are not particles in the traditional sense. They are the lowest possible energy excitations of the gravitational and electromagnetic fields, so gentle they barely exist. They are the quantum equivalent of a nearly inaudible hum. The theory proposes that whenever matter or energy falls into a black hole, it disturbs this quantum field at the horizon, leaving behind a specific pattern in this soft hair. It is like a stone dropped into a still pond. The ripples are the information about the stone's size, shape, and impact encoded in the water's surface. In this case, the falling book from our earlier mystery would create a unique, intricate pattern in the black hole's soft hair, a permanent record etched onto the boundary. This offers a potential escape from the information paradox. The information is not lost inside the singularity. It is preserved right there on the surface, stored in the specific arrangement of this zero-energy fuzz. The evaporation process, the Hawking radiation, would then be subtly influenced by this stored information. As the black hole glows and shrinks, the soft hair would imprint its data onto the escaping radiation, like a complex stamp on every outgoing particle. In this view, the information is not destroyed. It is merely scrambled into a code so complex it appears random, but is in principle retrievable. This has sparked intense debate within theoretical physics. Is soft hair a real physical solution, or is it a mathematical mirage? Critics argue that these zero-energy excitations might be too soft, that they cannot carry the rich, complex information required to describe everything that falls in. They might be what physicists call pure gauge, a mathematical redundancy that has no physical consequence, like describing the same object in two different coordinate systems. The information might be recorded in the hair, but in a way that is fundamentally unmeasurable from the outside, rendering it useless for solving the paradox. The research continues, with physicists exploring whether enough information can be stored in this soft fuzz to account for a black hole's immense entropy. It is a race to see if this elegant idea has enough substance to tame the infinite. The answer will determine if a black hole's memory is written in a language we can one day learn to read, or if it remains forever locked behind a veil of quantum silence. Some of the most powerful bullets in the universe are not made of metal, but of atomic nuclei. These are ultra-high-energy cosmic rays, particles that slam into our atmosphere with energies millions of times greater than anything we can create in the Large Hadron Collider. A single one carries the kinetic energy of a professionally thrown baseball, all compressed into a subatomic speck. For over a century, their origin has been a profound cosmic whodunit. The primary suspects are the most powerful engines we know, active galactic nuclei, where supermassive black holes are actively feeding. The chaotic environment around these monsters is a perfect natural particle accelerator. Imagine the colossal magnetic field surrounding the black hole's accretion disk and jets. A charged particle, like a proton, can get caught in these fields and be whipped around, gaining a tremendous boost in energy with each pass, much like a stone being spun in a sling before release. After countless cycles near the event horizon, the particle is flung out into the universe at nearly the speed of light, a cosmic ray of unimaginable power. The central mystery is not just how they are accelerated, but why we struggle so much to find their source. The clue lies in their electric charge. Because cosmic rays are charged particles, their paths are hopelessly twisted and bent by the magnetic fields that permeate the vast spaces between galaxies. By the time one reaches Earth, it is impossible to simply trace its trajectory back in a straight line to its origin. It is like trying to find the source of a particular leaf caught in a hurricane by looking at where it finally landed. The particle itself is a messenger that has forgotten its own address. This is where the new era of multi-messenger astronomy becomes our most powerful tool. We cannot rely on cosmic rays alone. Instead, we must become cosmic detectives, correlating their arrival with other, neutral messengers that travel in perfect straight lines. When a supermassive black hole accelerates a cosmic ray proton, that proton will often collide with other matter or light, producing two other signals, gamma rays and neutrinos. Gamma rays are high-energy photons of light, and neutrinos are ghostly, nearly massless particles. Crucially, both of these travel unaffected by magnetic fields. If we can detect a high-energy neutrino from a patch of sky, and at the same time observe a flare of gamma rays from an active galaxy in that same direction, and then also measure an influx of cosmic rays, we have our smoking gun. This trifecta of evidence is what finally pins the crime on the black hole. Each detection is a piece of the puzzle, and together they are beginning to draw a map to the universe's most powerful particle accelerators, hidden in the hearts of galaxies ruled by darkness. A star's final scream might be permanently etched onto the black hole it becomes. This leads us to a radical new way of thinking about these dark giants, the black hole DNA analogy. It challenges the classical no-hair theorem head-on, proposing that a black hole is not a simple, forgetful object. Instead, it might retain a unique fingerprint, a specific set of initial conditions inherited from the star or gas cloud that gave it birth. The chaotic, nonlinear violence of gravitational collapse is not a perfect eraser. Certain properties of the progenitor, like its detailed shape, its internal magnetic field structure, or the precise turbulence in its core, could leave a permanent imprint on the resulting black hole's gravitational field. Think of it like a potter shaping clay. Two lumps of clay with the same mass can be thrown onto the wheel, but the potter's specific hand motions, the pressure of their fingers, and the speed of the spin will create two pots with subtly different forms, unique ridges and curves that tell the story of their creation. In a similar way, the collapse of a star is an infinitely more complex process, and its unique wrinkles in space-time might not be entirely smoothed away by the formation of the event horizon. These would not be the three simple numbers of mass, spin, and charge, but far more intricate signatures, a cosmic genetic code woven into the fabric of the horizon itself. Researchers are now using immense numerical simulations to test this idea, modeling the most realistic stellar collapses possible with supercomputers. They are searching for any sign that a distinctive gravitational wave signature, a specific ring in the black hole's final tone, correlates with the properties of the star that died. If such fingerprints can survive the violent birth, it would completely reshape the information paradox. Information would not need to be lost or scrambled. It would be preserved from the very beginning, encoded directly into the black hole's structure. The event horizon would not be a blank slate, but a living record of a cosmic life, a tombstone carrying the detailed story of its own origin. That first ghostly image of a black hole's shadow was a triumph of human ingenuity. It was not a picture of the black hole itself, which is impossible, but of its silhouette against the fiery backdrop of its own accretion disk. The shadow is the black hole's dark heart, a region where light rays, bent by impossible gravity, spiral inward and are lost forever. This creates a perfect circle of darkness, a hole punched out of the brilliant light, surrounded by a bright, lopsided ring of photons that just barely manage to skim the edge of the abyss. The precise size and shape of this shadow are a direct test of Einstein's general relativity. The theory predicted a nearly perfect circle for the black hole in M87, and the image confirmed it with stunning accuracy. Yet, this very success opens new mysteries. The ring of light is not symmetrical. One side is markedly brighter than the other, a feature caused by the mind-bending effects of relativistic beaming. As the superheated gas in the accretion disk whirls around the black hole at nearly light speed, the side spinning toward us appears dazzlingly bright while the side spinning away is dimmed. This asymmetry is a direct window into the ferocious orbital dance at the event horizon, but the image holds deeper puzzles. The exact thickness of the bright ring and the sharpness of the shadow's edge are not fully understood. They are governed by the complex behavior of the magnetized plasma in the disk and the powerful magnetic fields that are thought to launch the black hole's colossal jets. We are essentially seeing the footprint of the jet launching mechanism itself. Future observations with more telescopes added to the Global Event Horizon Telescope network will provide even sharper images. We will watch this shadow flicker and change over time, tracking blobs of plasma as they make their final orbits. This could allow us to map the chaotic magnetic fields and witness the precise moment when material is either swallowed or channeled into the jets. Each new pixel in this cosmic portrait brings us closer to understanding the fundamental laws that govern matter and energy in the most extreme environment the universe has to offer. This intricate dance between darkness and light extends far beyond the black hole's event horizon. The supermassive black hole at the center of a galaxy is not a silent tenant, it is an active architect. Astronomers have uncovered a startling cosmic correlation. The mass of a galaxy's central black hole is intimately tied to the properties of the galaxy's central bulge, the dense collection of stars at its heart. The more massive the bulge, the more massive the black hole. This is not a coincidence. It points to a deep, symbiotic relationship, a coevolution that has shaped the universe over billions of years. The central mystery is the nature of this partnership. How does a relatively tiny object hidden in the galactic core communicate with and influence an entire galaxy 1,000,000 times its size? The answer appears to be feedback. When a supermassive black hole actively feeds, it does not do so quietly. The immense energy released from its accretion disk and its powerful jets pours into the surrounding galaxy. This energy can heat up vast reservoirs of cold gas, the very fuel needed for new stars to form. In this way, the black hole acts as a cosmic regulator, a gravitational thermostat. A burst of feeding activity can blow away star-forming gas or heat it so much that it cannot collapse, effectively shutting down star formation in the galactic center. This process explains why we do not see ancient galaxies growing without limit. The black hole, through its violent meals, puts a brake on its own growth and the growth of its host. But this leads to the ultimate chicken and egg problem. Which came first, the galaxy or its dark heart? Did the galaxy form first, with the black hole growing later from the gas that sank to the center? Or did a primordial black hole seed form first, acting as a gravitational anchor around which the very first stars and the galaxy itself coalesced. The light from the most distant quasars suggests that supermassive black holes were already in place when the universe was very young, implying a rapid and intertwined growth. Perhaps they grew up together, the galaxy feeding the black hole, and the black hole, in turn, governing the galaxy's development through its energetic outbursts. This cosmic feedback loop is what sculpts the majestic spiral and elliptical galaxies we see today. A galaxy and its black hole are locked in a gravitational conversation, a dialogue of creation and destruction that dictates the life cycle of stars and the very structure of the cosmos itself. The violent merger of two black holes sends shudders through the cosmos, ripples we can now feel as gravitational waves, but the final moment of collision is not the end of the story. As the new, larger black hole settles into its form, it vibrates like a struck bell, emitting a final, fading hum of gravitational waves known as the ring-down. This phase is our most direct probe of the newborn black hole's event horizon. The specific frequencies and decay rates of this ring-down are the unique signature of the horizon's size and shape, a direct test of whether the resulting object truly is the Kerr black hole predicted by Einstein. Any deviation from this expected tone would be revolutionary, hinting at exotic physics or even that the object is not a black hole at all, but something even stranger. Beyond the ring-down, the mergers themselves present a profound puzzle of origins. How do these binary black holes find each other in the vastness of space? We see evidence for two possible formation channels. In isolated binary evolution, two massive stars are born together, live their lives as companions, and eventually both collapse into black holes that slowly spiral together over eons. In dynamical formation, lone black holes in dense stellar environments like globular clusters gravitationally pair up through chaotic cosmic dances and collisions. The gravitational wave signals carry subtle clues about which path was taken, from the alignment of the black holes' spins to the eccentricity of their orbits. But the data has delivered a stunning surprise: the sheer mass of some of these black holes. We have detected black holes with masses far greater than we thought possible from a single collapsing star. Some weigh in at over 50, even 80 times the mass of our Sun. This shatters our models of stellar death, which predict that very massive stars should be completely blown apart by pair instability supernova, leaving nothing behind. Their existence forces a radical rethink. Were these black holes born so large from primordial stars of pure hydrogen and helium? Or are they themselves the products of previous mergers, black holes that cannibalized others in a dense stellar environment to become the cosmic heavyweights we now observe? Each ripple in spacetime is not just a signal, it is a fossil record of a violent history, a story of life, death, and rebirth written in the fabric of spacetime itself. This very act of scrambling information could be the universe's ultimate calculation. The wildest frontier of black hole physics suggests these gravitational pits are not just simple objects, but the most powerful quantum computers in existence. Think of the complex, chaotic mess of data from every star and planet that falls inside. Quantum information theory proposes that a black hole does not just store this information, it constantly processes it. The interior volume, according to some calculations, performs an unimaginably complex computation, with the quantum states of all the infalling matter acting as the input bits. The concept that links this process to gravity is called computational complexity. In simple terms, it is a measure of how hard a computation is, how many logical steps are required to transform the input into the output. Remarkably, some physicists have found that the computational complexity of the information inside a black hole appears to be directly proportional to the growth of the black hole's interior volume. As more matter falls in, the complexity of the calculation increases, and the space inside the black hole expands to accommodate it. This frames the black hole's entire evolution not just as a gravitational collapse, but as a dynamic computational process. The event horizon is the machine's shell, and the churning spacetime within is its processor, running the most intricate program reality allows. This bizarre idea offers a fresh perspective on the information paradox. The information is not lost, it is merely transformed through this ultimate computation, becoming so deeply encrypted in the complex quantum state of the black hole's interior that it appears random and lost to any outside observer. It connects back to the holographic principle in a profound way. The two-dimensional horizon holds the simple, encoded data, like the lines of code for a program, while the vast three-dimensional interior is the active execution of that program, the unfolding calculation itself. We are left to wonder if gravity itself is not a fundamental force, but an emergent property of this underlying quantum computation, a shadow cast by the universe constantly processing its own information at the most extreme scale imaginable. So we arrive at the final, all-encompassing mystery, returning to the book we threw into the abyss at the very beginning. All of our questions, from singularities to soft hair, converge on this single point. What is the ultimate fate of information that falls into a black hole? The most radical proposals suggest it does not vanish, but embarks on a journey far stranger than we ever conceived. One of the most elegant ideas is known as the ER equals EPR conjecture. It proposes a deep and beautiful connection between two seemingly unrelated concepts in physics. EPR refers to quantum entanglement, that spooky connection where two particles can instantly influence each other across vast distances. ER refers to an Einstein-Rosen bridge, which is the formal name for a wormhole. The conjecture boldly states that these are not two different things, but two different descriptions of the same reality. Every pair of entangled particles is connected by a microscopic wormhole, a tiny tunnel through the fabric of spacetime. For a black hole, this offers a breathtaking solution to the information paradox. When a particle and its entangled partner are pulled apart at the event horizon, they are not truly separated. They remain connected by a wormhole, a secret passage that preserves the information. The book falling into the black hole is not lost. Its information is simply transferred through this spacetime tunnel, potentially to another region of our universe or even to another universe entirely. Another mind-bending possibility is that black holes do not store information at all, but instead give birth to new realities. In this scenario, the immense energy and complexity of the collapsing matter does not crush into a singularity, but instead triggers a new Big Bang, creating a baby universe that branches off from our own. The information from the book would not be destroyed. It would become the fundamental seed, the initial conditions for an entirely new cosmos, forever inaccessible to us but preserved in the laws of that new reality. Then there is the possibility that Stephen Hawking was right all along, but we have been misinterpreting his work. Perhaps the information is not lost in the black hole, but is perfectly encoded in the Hawking radiation itself. The catch is that this encoding is so profoundly scrambled, so thoroughly mixed through quantum chaos, that it appears completely random. It would be like taking the complete works of Shakespeare, running them through a cosmic paper shredder, and then tossing the confetti into a hurricane. Every letter is still there, but the information is spread across the entire cloud of radiation in a non-local way, with no single particle holding a recognizable piece. Reconstructing the original text from the outgoing radiation would be a computation of unimaginable complexity, requiring a computer larger than the universe itself. These are not just wild speculations, they are serious attempts to reconcile the fundamental laws of our universe. They force us to consider that information may be the most indestructible substance in existence, capable of surviving even the total gravitational collapse of a black hole by transforming, tunneling, or birthing new worlds. The fate of a single book could be the key to understanding whether our universe is one among a vast multiverse, or if every black hole is a locked door to another dimension, its key hidden in the faint, cold glow of its own evaporation. We have journeyed through 30 profound mysteries, from the silent darkness of the event horizon to the fiery paradox of information's fate. Each question reveals that black holes are far more than cosmic vacuums. They are the ultimate laboratories, testing the very laws of physics at their breaking point. A common thread weaves through every enigma, the fundamental tension between the quantum world of the very small and Einstein's grand vision of gravity and spacetime. This conflict, centered on the elusive nature of information, is the great battleground of modern physics. It is a puzzle that forces us to question the nature of reality itself, from the holographic encoding of three-dimensional space on a two-dimensional surface to the possibility of wormholes linking entangled particles. The journey does not end here, it is merely beginning. New eyes on the cosmos, from the next generation of gravitational wave observatories to ever more powerful telescopes peering into the hearts of galaxies, are gathering data right now. The solutions to these mysteries are written in the ripples of spacetime, in the faint glow of Hawking radiation we hope to one day detect, and in the intricate dance of particles at the edge of oblivion. Stay curious. The greatest discoveries in our understanding of the universe lie not in the answers we already have, but in the profound questions that remain, waiting in the dark for a spark.